Okay, welcome back. Glad it's Friday. I hope you're glad it's Friday. It gives me a day to rest up. It is Friday the 13th. I didn't realize on Wednesday you all had a exam on 9/11. So, but I heard most of you guys may not have been born when 9/11.
No, you're not quite there yet.
Not yet. How old were you?
Like 2.
Yeah. I don't remember anything before high school. Even my high school years, I didn't graduate.
I don't remember high school.
I'm told it's Mid-Autumn Festival. It's a full moon. It is a full moon, I think, tonight.
Oh God.
It's right. Full moon.
So it's full moon and Friday the 13th.
Yeah.
We're dead. We're just dead.
So you guys stay off the roads. Don't party hard. I heard it's full moon time is also time when the emergency rooms and hospitals are more busy.
That's been proven false.
I didn't celebrate Mid-Autumn Festival in my childhood growing up, even though I'm of Chinese descent. But in 2009, my wife and I spent a year in Taiwan, which is a Chinese place, and we discovered that they have interesting holidays and stuff, and one of them is the Mid-Autumn Festival. And at the time, we learned that Taiwanese people don't barbecue. They don't grill out, except on this day. And we went to the stores, and everything had been taken off the shelves, except bags and bags and bags. All you can find on this were little aluminum trays and Kingsford charcoal. And that day, it seemed like the entire country was grilling all over the place, under the highway bridges, on street corners, everywhere, and everywhere you went, it was just like this cloudy, smoky day. It was like the city was on fire. I was told they may have outlawed it because of the pollution. And then the next day, life went back to normal. Fried Chinese food, no more grilling. So that was my experience with the Mid-Autumn Festival. I do know that they have a particular cake that they eat. It's a round cake. They call it a moon cake, like full moon. I guess it's a Chinese version of a moon pie. Except moon pies are much better, in my opinion, because they're marshmallow and chocolate. So that's today. But this is what our focus is. This is another exercise in the Ralph Hurwitz. So we will use, this is another practice of the Ralph Hurwitz analysis. Okay, so we introduced Ralph Hurwitz on Monday. I did an example. I just want to do another example today. Okay. So we're given a system. This is its input. This is its output. This is the model. And depending on what these coefficients are, gamma 0, gamma 1, gamma 2, and k, we want to determine whether or not the system is stable. Okay. So the first thing we can conclude is that, let's make some conclusions about this. K can be anything. No restrictions. It can be no reasonable restrictions. No, it can be positive. It can be negative, because it's in the numerator. Obviously, if it's negative, it's going to change the sign of the output, but it doesn't affect the stability. It doesn't cause the system to blow up. So what we have to do is we have to study the denominator, the characteristic. Okay, so we need to study that characteristic. So we need to study s cubed plus gamma 2 s squared plus gamma 1 s plus gamma 0. So this is what we're going to do. We're going to set up a Ralph Hurwitz analysis and then see where that leads us. So let's construct the Ralph table. Okay, that lists all the rows. It's just convenient for bookkeeping to keep track of things. Then we populate the array, first two rows, with the coefficients of this polynomial. So the first coefficient here is implicitly a 1, because
Okay, so I put that 1 right here, put gamma 2 here, gamma 1, and gamma 0. So we started the array. Next thing we need to do is we need to calculate this coefficient. I'm going to call it B0. Okay, I'll calculate here. B0 is equal to a 2 by 2 array constructed of these 4 elements. 1, gamma 2, gamma 1, gamma 0. Got to put a minus sign in front of it, and then I had to divide by gamma 2. Okay. So that is equal to gamma 1, gamma 2, gamma 1, gamma 2, minus gamma 0 divided by gamma 2. Let's calculate this one, B1. The array is constructed, the first column doesn't change, so it's 1 and gamma 2. I've used up these 2 elements, the second, so I need to take the next column over. The next column over is 0 and 0. And then I divide by gamma 2 again. The bottom doesn't change, this term doesn't change. The first column doesn't change, it's the second column that changes. But this is equal to 0. So this is equal to 0. And then let's do this one. This is C0. Let's calculate C0. And so it's going to be a 2 by 2 array constructed of these 4 elements. Gamma 2, B0, gamma 0, and 0. And then I can divide by B0. And I get the result, this is gamma 0. Let me leave that up for a few minutes so you can copy it, and then I'm going to rewrite it on the next page on a clean sheet of paper without all the algebra and just have the answers there. All right, so I'm going to clean up. This is what we have. All right, let's take a look. A reminder, notice that this element is the last element in an even powered row of S. This is also a last element in an even powered row of S. These should be the same. Okay, that's just a math check. It's a math check, or it's a shortcut. If you don't want to do calculations and you know where they belong. Even powered rows have the same last element. All right, so now let's apply the criteria. The criterion says that the denominator has no roots in the right half plane. Or if you want to put a shorthand, you could say no poles. Poles are the roots of the denominator. No poles in the right half plane. Right half plane. It has no poles in the right half plane if and only if there are no sign changes, in the first column. And by first column, I'm referring to this column right here. Okay. So the conclusion is, well, we look at the first element, we see that's a positive number. So if that's a positive number, then all these better be positive numbers. Okay? We can't allow any sign changes. The number of poles in the right half plane is equal to the number of sign changes. Okay? So that's another way to put it. The number of poles in the right half plane, the number of roots in the right half plane is equal to the number of sign changes. We don't want any sign changes because we want a stable system. So our conclusion is, from this statement, is that we can make these conclusions. We can conclude that 1 is greater than 0. That's not a conclusion to be made, but gamma 0 must be greater than 0. Gamma 0 has to be greater than 0. Another thing that we can see is that gamma 2 has to be greater than 0. And this expression, gamma 1, gamma 2 minus gamma 0 over gamma 2 has to be greater than 0. Now we can clean this up a little bit more, because if gamma 2 is positive, then what I can do, multiply on both sides by a positive number, that doesn't change anything. And so therefore my conclusion is, since gamma 2 is greater than 0, I can conclude that gamma 1, gamma 2 minus gamma 0 is still greater than 0. Or gamma 1, gamma 2 is greater than gamma 0. And since gamma 2 is positive, is a condition, then I can conclude that gamma 1 is greater than gamma 0 over gamma 2. So I have this conclusion, wait a second, yeah, this conclusion, and from the earlier conclusion also, K is anything. Okay, any questions? The key element is to kind of understand what Rouse-Hurwitz criterion tells us. It tells us the number of roots in the right half plane. We want that to be 0. So we need to know how to set up the array and then calculate. Okay, very good. I'm going to hand back exam number 1. I'll post some solutions on Canvas this weekend. I'm working on them right now, cleaning them up so they look decent. And then I'll hand back the exams right now to you, though, and you can take a look at the solutions. The class average was really good. It was 85 something. We had a number of perfect papers. I must be getting easy in my old age. Okay, Mr. Sun, Haoshang Sun.
It's not like everybody knows what
Xu Lin. Xu Lin. You just raise your hand, I'll come back to the wall. Carter Green. Kyle Sanders. Macy Paris. Philip Champion. Kitai Wu. Wu. Tanner Vasey.
Here.
Vasey. Will Broussard. right, so we're gonna see how my Italian is. Maria Vittoria Orapaio. The L's are not silent. Orapallo. Tyler Ward. Zaxin Liu.
Whatever you started.
Hamza Khan.
Well, no, you bring it.
Jin Kwan.
You multiply everything by R. You get. Yeah, that's that.
Sean Honeycutt.
R.
Case Cole.
No, seriously, multiply. Look, you multiply by R on the top and R on the bottom. That's the same as 1. And then this goes to 1, this goes to R over S, and this goes to 1.
Brandon Wallace.
This is not equivalent.
Chin Chin.
Well, the problem is you flipped it.
Emma Little. I'll come over.
You slid what?
Randy Fields.
You can't slide the numerator down. Maybe if you merge them before.
Charles
So,
Moncrief.
like, we merged these, right? We get our. Can we write on different?
No.
Nicholas James.
RSL.
Nelson
Now
Whitman.
you can move it as much as you want.
Gregory Cook. Cook.
I think he said Nicholas James.
Andrew Ray. Alexis Daniels.
Dr. Hung, did you say Nicholas James? I think that's me, Jones. So 100.
Jones, I'm sorry.
Okay.
Andrew Ray.
Oh, wait.
With Emerald.
RCS plus.
Yes. Yates. With Emerald. Thomas Murphy. Thomas Murphy. Mac
you solved
Campbell.
You got it upside down.
Holden Covington. Holden. Jack Satterfield. Davis Early.
Okay, so the formula is should be. Wait, see, no. This is wrong. This is distinctly wrong. Okay,
Ryan
okay.
Booth.
So B out is equal to B in times.
Jacob Garcia.
This is
EC Lou.
This right here. You see, agree with this? Because this is current division.
Yes.
Voltage division. And then you just divide by V and you get exactly the same.
Robbie Cohen.
Wait, that's my turn.
Better.
Fantastic.
Nicholas Wrist. Wrist.
Why are you sneaking it? Why are you sneaking it?
Santosh Standina.
Now you got a feather nap. I have to think I have his number saved.
Leonard.
It's not like he'll answer. Now we got one check on this whole page. He just gave up. Fuck up B-Tran. You should. Oh wait, yours is by 2. Okay, so first one's the current.
We got a few minutes. Let me go ahead and just kind of talk a little bit about the exam. I'll put details again. As I said, I'll post them this weekend. The first problem is a circuit analysis problem. We want to find the relationship between two signals. One is called the input and one is called the output. And so I'm looking for several things here. First of all, that we haven't forgotten everything we learned in linear systems and circuit analysis. The problem is complicated by the fact that, and we need to understand, the relationship between input and output. We should eventually be getting some sort of relationship, some sort of notation that looks like V out over V in. Okay, so that's I'm looking for that, and then I'm looking that we know how to analyze a circuit. So this particular circuit has two inputs. So then how do you handle two inputs? We want to remember to use superposition. So how do we apply superposition? You kill all the sources but the one of interest. So the one of interest is this one. So we kill the other source. When we kill a current source, it becomes a open circuit. So it just goes out of the picture. So now the picture is easier. Now I'm interested in the output voltage, so it would make sense to write a nodal equation. I need to write a nodal equation for this node and one for this node. But I don't need really to write an equation for this one because the node voltage is always going to be this. So that further reduces the problem. I just need to write an equation for that node right there. And so we do that. That's what this individual has done. And then to transform it, does a little bit of algebra. Okay. If there were problems here, it was circuit analysis problems. We forget maybe this. Okay. Your version of the exam may be a little bit different. You may have had a circuit that has an inductor. The inductor and the capacitor are swapped. Okay, so still the same principles. You got to know how to simplify it. The next question asks, what do you do if there's an initial condition on something here? And the thing that I'm looking for is the realization that initial conditions do change the behavior of the system, but they don't change the transfer function. So I'm looking for some words that say it's not affected. I think just about everybody got that one. And I think just about everybody got the last problem, is where we have a differential equation, some derivatives, some integrals, and we need to transform that. And so terms like derivatives, like y double dot becomes s squared y of s, and integral becomes a divide by s, and then the coefficients carry along in scaling. And then what we do is you do some algebra. Yes, question?
Are you able to get rid of that 6s squared since?
Am I get rid of?
Zero?
I'm sorry, I'm not following. Am I getting rid of
So
what?
you got there one of the conditions that u prime is 0, correct? So does that not make 6u prime also 0?
It's U prime
This?
is 0, 0.
This one?
Yeah.
Okay, so your question, should I make this?
That's
Make
not
it 0.
the initial condition, is it?
It's just an initial condition.
But it
U dot
doesn't-
itself is not 0, but U dot's initial condition is 0.
Oh, is that the?
It's not written
Yeah.
as an initial
Yeah, it's
condition.
written as the entirety of the function to 0.
Yeah, it says the initial condition.
Yeah.
Okay, so one has to understand this is an equation. These are not a set of initial conditions. They apply at the initial condition, but they have to also apply it all the time. So I think just about everybody did pretty well on that one as well. The next problem is about block diagram algebra. So we basically want to take these feedback systems and reduce them. The first one was just to test the fundamentals to see if we understand what to do about the signs and how to handle them. So I'm looking for something like 4 gain over 1 minus the loop gain. And this person got that one okay. In the bottom, the loop gain here is G1, G2. That sign is correct. But there, the 4 gain, they dropped a minus sign. Okay, this problem is a little bit more complicated because it's got multiple loops. And so you got to figure out how you decide to reduce this. You need to reduce this because our formula is just for a single loop. This is a multi-loop system, and so we cannot apply the formula directly. Now here is where you could get varying answers they all need to get to the end, to the right answer at the end, but how you approach it can be a little bit different. You notice that this particular individual decided to say, I'm going to try to reduce it, and he very carefully drew a line around like this, but he included that minus sign. Okay, and frankly, he's going to get himself into trouble. Because later on, he's going to have to take into consideration what is the signal path this way, and he's ignored this sign, or he needs to take care of that sign very well. So what he's saying is going this way, this signal looks like it's got a minus sign. But going this way, he's absorbed the minus sign here, and so going in here now, this looks like a plus sign. So by circling it like this, he's created a little bit more work, or maybe it was she who could produce some more work. You may have decided not to put that minus sign in and drew your loop like this, in which case, regardless of whether you're going this way or this way, there's a minus sign. Or you may have decided to take a loop around this way, in which case you're absorbing the minus signs for everything inside. And so here I had to study real carefully what route you went. And most people, if they had problems on this one, was dealing with this sign. So you gotta look at it carefully. It is possible that I misgraded yours, so if you think you dealt with the sign correctly, come to my office and I'll give you an oral relook at the thing. The other problem is sometimes we miss a sign as we go around the loop. You go around the loop, you gotta account for all the signs. Clearly there's a sign here. Occasionally people miss this one. And then, depending on how they drew the circle here, you have to figure out, is this sign inside the model or is it outside the model, and how do I account for it? So that has to be addressed carefully. Most errors, if there were errors, were sign errors. Just like this individual, he's made some sign errors because of this. Again, once it's reduced, then it's still a matter of just understanding what is the forward gain divided by 1 minus the loop gain. The next problem dealt with two issues, stability and step response. Okay, so we have to check for stability of a control system. This says consider the control system block diagram. The control system implies there's feedback, so it looks like this. But I give you just the model of this box. And then so the first thing one has to do is find the model of the control system. And so if there were some problems, there were sometimes people just forgot to calculate it, the control system model. They just analyzed this box alone, and that would not be correct. Once you've done that, then you can analyze it. There's two problems. There's a first order problem. The first problem is a first order model. The second one is a second order model. He's got to calculate it. He's done the calculation correctly here. He's done the calculation correctly here as well. And then from there, you can find all the properties and then sketch the response. In this particular case, there was a response like this. Depending on your exam, you would have a different model here you have to deal with. Same is true down here. Your model may be slightly different, so you get some different numbers there. And then the last problem has to deal with Z-transform concepts. How to go from a sequence of numbers to the Z-transform. And so this is the sequence of numbers for different k's. He's actually labeled his k's here. K0, K1, so on and so forth. So this is the k sample index starting with 0. And then the Z-transform definition simply says that I have powers of Z. So this is 5, z to the 0. Z to the 0 is just 1. This is the second sample. That's why it says z to the minus 2, scaled by 4. This is the fourth sample, scaled by 3. And this is the seventh sample, like so. The next one is give the Z-transform for the shifted sequence. Depending on your exam, I may have said shifted by 2 or shifted by 3. The idea here is all you need to do is write this. Okay? You just need to multiply by z to the minus 3 because this is shift of 3. And then you can take your risk and write your algebra. Okay? But if you left it at there, I understood what you did and I gave you full credit. If you decide to go and demonstrate your algebra skills, then I graded the algebra. Okay, this is a slightly different Z-transform. It's written in what we call closed form. The first question says, okay, if I give you a Z transform, what is the transform for the underlying sequence if I shift it by a certain number? And so again, I said in this particular case, it was shifted by 3. On your exam, it may have been shifted by 2. So again, there's the answer right there. And that would have gotten you full credit. Or you could demonstrate various algebra skills. And probably the hardest problem is this one. And I'll go ahead and show it to you because he did do it correctly. Find the sequence of numbers. I want you to go inverse Z transform. It doesn't look like the first problem where it's written out and you can just pick the coefficients off. This problem is written in closed form. And so the suggestion was to take that expression and do long division. And so you set up the long division and you do it. So you say, what needs to multiply this to annihilate this term? You need to multiply 1. So 1 times Z minus 9, 0.9 gives you Z minus 0.9. You do the subtraction, you get 0.9. Now you ask yourself, what do I have to multiply this to get rid of the 0.9? And then I say, I need 0.9 Z to the minus 1. 0.9 Z to the minus 1 multiplying this gives me a 0.9 minus 0.9 squared Z to the minus 1. Do the subtraction. Continue on. And now this thing starts coming out. So this is the Z to the 0 term, Z to the minus 1, Z to the minus 2, and you can continue going on. The coefficients now for the first 3 terms, he's finished. This one, and this one. Okay, any questions? I suggest you take a look at your exam carefully, make sure I didn't make an error. I have been known to make some errors, so if you think I made an error on your thing, then on your paper, let me know. I will again try to post the solutions this weekend. Question? Yes?
What are office hours?
When are office hours? I plan to be here all day. I have a test. I have another class right after this one, so I won't be there from 10 to 11, but I basically will be here. I will be here today for sure until 3 because I have to collect a bunch of 30, 40, 30, 50 memos upstairs at 3 o'clock. But basically I'm here Monday through Friday outside of classes. Okay, that's all I have for today.